Yes, welcome to Rajagiri online classes. I am Santhi, Assistant Professor, Department of Electrical and Electronics Engineering. Last session we are handling the topic on power system analysis, module 5. The topic was on economic dispatch and unit commitment, and I started with the introduction to what is economic dispatch, and we were seeing what is the economic division of plant load among the different generating units within a plant. So it could be taken as an optimization problem, and I can say the solution is, the objective of the function is to reduce the total cost on the plant, which is nothing but the summation of the total cost, individual cost of each and every unit, n number of units within the plant, and it is being subjected to the equality constraint of the total demand should match with your total generation, as we have neglected the transmission losses. Okay, so the condition to be satisfied is the plants has to be maintained with equal incremental cost. So that's the condition we are to be satisfied, so that you can economically divide the load. So the condition is dCA by dPA equal to lambda. All the plants are maintained with equal incremental cost for n number of units within a plant, and also we have to use up the power balance equation. So we have got totally n number of variables, which is P1 to Pn plus one variable is your lambda. So totally I have got n plus 1 variables, and here we have got n number of equation, dC1 by dP1 equal to lambda, dC2 by dP2 equal to lambda. Likewise we have got till dCn by dPn equal to lambda. So I have got n number of equation here, and one is your power balance equation. So totally we have got n plus 1 variables and n plus 1 equations. Okay, so we have to solve this. So the intention is to make the main condition for your minimum cost of operating is to go with the equal incremental cost rule. That's what we are doing, and we have a power balance equation also. Now let's see how to solve your problems under this concept. So let me consider the first example problem that you are going to work out. Here you have got 2 units is given for this plant. So this plant has got 2 different units, and the cost equation of these 2 different units is mentioned here. So C1 is the first cost of the first unit, and it is in terms of its generation P1, and C2 is the cost of the second unit, and it is in terms of its generation, which is P2. So this is the cost equation of the 2 plants, and the allocation, the load allocation is mentioned that you have to distribute a total load of 162.5 megawatts among these 2 units. Okay, and you have been asked to calculate what is the daily loss if the loads are loaded equally. So we have to first go for a case where we have an equally lambda criterion has to be adopted, and same we will see how to equally share the load. Then we will see what is the loss that is incurred when we go for an equal sharing. So let's start solving the problem. So let me use the whiteboard. So the cost equation of the first plant is given as C1 is 0.4 P1 square plus 160 P1 plus K1. So it is your alpha coefficient, beta coefficient, and this is your gamma coefficient, and the unit is going to be rupees per hour. This is the dimension of this. Second unit, it has got 0.45 P2 square plus 120 P2 plus K2. So the same unit, rupees per hour. Okay, so once we have got the cost equation, the first step we will do to find is to find what is the incremental cost of that plant. So we have to take what is IC1. IC1 means incremental cost of the first plant, which is dC1 by dP1. So just differentiate this equation with respect to P1. So you get 0.8 P1 plus 160, right? If we differentiate with respect to. So, and the unit will be in rupees per megawatt hour. Is it clear? Because this is rupees per hour, this is in megawatt. So totally the unit will be in rupees per megawatt hour. Similarly, let me find out what is the incremental cost of the second plant, which is your dC2 by dP2, and of course I try to differentiate this equation with respect to P2. So it is 0.9 P2 plus 120, and of course the same unit rupees per megawatt hour. Okay, now from this 2 equation, so it is, what is your equal lambda criterion says? Equal lambda criterion is the solution. Okay, so as per the equal lambda criterion, it says that your incremental cost curve of the first plan must be equal to incremental cost. Okay, all must be same. All the plans has to have a equal lambda criterion. We have to adopt. This is the solution for this optimal scheduling. So IC1 equal to IC2 equal to lambda. So equate this. So we have the equation 0.8 P1 plus 160 equal to 0.9 P2 plus 120 equal to lambda. So totally, you see, and from this equation, so this could be equated separately lambda, and this could be equated to. So when I equate this to lambda, so what's the equation? P1 will be equal to lambda minus 160 by 0.8, and P2 is going to be lambda minus 120 by 0.9. So if I know the value of lambda, I'll be able to calculate what is P1. Now this is one set of equation. Then another equation is, we have got, this is two equations. So totally we have got three variables, P1, P2, lambda. And this is one set of equation. And another set of equation is your power balance equation. So power balance equation says PD minus summation of your generation. Summation of your generation is P1 plus P2 is equal to 0. Now, in our case, what is the load? Load is actually, the load is given as, PD is given as 162.5 megawatt. Okay, so in that case, I'll have 162.5 megawatt minus P1 plus P2 will be equal to 0. This is the case. Okay, so how could I write this equation? So I can write P1 plus P2. So substitute this value of P1 plus P2 in this equation, and you can calculate. So I take this equation P1, so it is lambda minus 160 by 0.8, which is P1, and P2 is lambda minus 120 by 0.9 can be taken as 162.5. So from this take the lambda coefficient, so it is 1 by 0.8 plus 1 by 0.9 equal to 162.5, and bring this up here, okay, plus 160 by 0.8 and plus 120 by 0.9. Okay, so based on this equal lambda criterion, so solving this, so if we take this coefficient, it comes as 2.3661 lambda, and this on simplification it gives you what is 495.833. Okay, so from this we can also find out what is lambda. So from this I will get what is lambda. Can get lambda value as 210. So this much 210, and this is nothing but the unit rupees per megawatt hour. Okay, so once I am able to calculate the value of lambda, from which I can use this value of lambda in this equation, and I can compute what is P1 and P2. Okay, so substitute this value of lambda in this two equation, from which you get P1 as 62.5 megawatt. And substituting the value of lambda of 210 here, we will get P2 as 100 megawatts. Okay, so we have lambda is 210, P1 is 62.5 megawatts, and P2 is 100 megawatts. Okay, so when I do your economical load division between these two plants in a plant, into this unit in a plant, you will get P1 as 62.5 megawatts and P2 as 100 megawatts. Now they have asked you to calculate what is the daily loss when I am comparing this with equal sharing. So the next stage will go with equal sharing. Okay, so the total load here is PD is equal to 162.5. Now if I am going on case which is your equal sharing. Okay, if I am going for equal sharing, then the total load P1 will be equal to P2 will be equal to 162.5 by 2, which is 81.25 megawatts. Okay, so it's on equal sharing, this has to go by. Now we have to compute what is the daily loss. Please note that this particular equation, cost equation is given in terms of rupees per hour. So how much rupees is being spent per hour, and they have asked you to calculate daily loss. So daily means we have got 24 hours a day. So when I compute what is your daily loss, and where the is given that all the two plants, 2 units within the plant is also operating for the entire 24 hours. So the total cost, how we have to work out the cost of both the plant, both the unit we have to work out. Okay, so the daily loss is calculated for 24 hours I have to take, which is your total cost. Okay, total cost is nothing but C1 plus C2, and with P1 and P2. With P1 and P2 it is equal load sharing. With this equation taking as 81.25 and substitute here this. Okay, so with P1 and P2 both values at 81.25. We have to find out the cost. Okay, and then subtract with the total cost when you have your P1 and P2 with lambda criterion, where P1 will be 62.5 megawatt and P2 is going to be 100 megawatt. Okay, so this is the total cost when on equal sharing, where P1 and P2 both takes 81.25 megawatts, and this is the total cost when using your equal lambda criterion, where P1 is 62.5 megawatts and P2 is 100 megawatts. So if I compute the cost, okay, so this equation, of course you have to substitute this value of P1 and P2 with this. So you get C1 and C2, sum of both, that will give you the total cost. Similarly, substitute P1 as 62.5 and P2 as 100 and sum of both. Okay, that will give you the total cost. Okay, so this will come around as 24. If you substitute and finding out, you will get this total cost as 28361.328. Okay, and of course when I substitute P1 here I have K1 and K2, isn't it? So I have one K1 and K2 here. Okay, similarly minus substituting this value of P1 and P2 in this equation with K1 and K2, I will be having this equation which is 28062.5, and I have that K1, K2 constants will still be there. But since it is a difference in between this cost, this both will get cancelled. Finally, this difference multiplied, okay, this difference multiplied by this 24, this daily loss can be computed as rupees 7171.87. Okay, if you define out the difference between these two values into 24, it gives you. So we have to see that the cost when I am doing equal load sharing, this is the cost when I am doing your as per your equal lambda criterion. So this comes with a loss, because when I do your equal load sharing, I have a loss of this much rupees per day. Okay, and it could also be done the other way around. If I want to do your, if you take this first, okay, then it will be taken as a daily profit. Okay, because 62.5, this is your equal lambda, this could be put first and this could be put second. Then once again you will be getting a negative value that indicates that this cost is lesser, that is I am going for a profit. Okay, so it could be calculated either as a profit or a loss. So here, since this is positive, it shows that the cost we get as per your equal sharing is more. Okay, and the cost when I get as per your equal lambda criterion is less, that is I am having a loss. So that's why we prefer to go by your equal lambda criterion. So this is what is being done in your example 1. Okay, next students, we shall move on to the next problem. Okay, and of course you can see that here no limits is mentioned, so we are not taking care about what is your inequality constraint is not mentioned here, because they have not given any information regarding the minimum or maximum generation. So we are not much worried about your inequality constraint. Okay, next we shall move into a problem considering this inequality constraint also. So let's work out for the second problem. So moving on to the second problem. So second problem, here we have mentioned it has got 3 units. Okay, it has got 3 units. We have given you the cost equation of the 3 units. Okay, so and all are 3 units within the plant. But here you see there is one information given on what is the minimum and maximum allowable generation. Okay, so you can find that here the minimum generation is 39 megawatts and the maximum is 150 megawatt, and you have been asked to schedule the load for two different cases. The first case is 320 megawatt and second case is 200 megawatt. So let's work out this problem. So we have got the three cost equations where I have C1 is given as 0.5 P1 square plus 215 P1 plus 5000. Okay, so that much rupees per hour. I have got C2. C2 is taken as 1 P2 square plus 270 P2 plus 5000, same rupees per hour. And you have got C3 which is 0.7 P3 square plus 160 P3 plus 9000. Okay, so in this case, as usual, the first step will be you have to calculate what is your incremental cost. So let me calculate the incremental cost of the first plant. So you have to DC1 by dP1. So it is nothing but 1 P1, right? Plus 215. So that much rupees per megawatt hour. Megawatt hour. Okay. Then similarly we have got your IC2 differentiating. So it is 2 P2 plus 270. Same, and then IC3 will be 2 times. So it is 1.4 P3 plus 160. Okay. So the unit is going to be same rupees per megawatt hour. So we have got the incremental cost. Now as per your equal lambda criterion, okay, as per your equal lambda criterion, we have IC1 must be equal to IC2 will be equal to IC3 must be equal to lambda. Okay, so as per the equal lambda criterion, we have to have the incremental cost of all these three must be equal to lambda. So from this equation we will have P1. Okay. So from this equation we will have P1. Okay, P1 can be taken as lambda minus 215 by 1, and P2 can be taken as lambda minus 270 divided by 2, and P3 can be taken as lambda minus 160 divided by 1.4. Okay, so these are the three equations for your P1, P2 and P3. Okay, and the other equation is your power balance equation. So power balance equation can be taken as the load demand. Okay, so we have been given with the load demand 320 megawatts. Okay, so let me go. Okay, so I have got case 1. Case 1, I have got a load demand of 320 megawatts. Okay, so my condition is your total generation. So PD minus your P1 plus P2 plus P3. This must be equal to 0. Okay, so we have got, and P1 plus P2 plus P3 is given by this equation. So I have taken lambda minus 215 by 1 plus lambda minus 270 by 2 plus lambda minus 160 by 1.4. This must be equal to demand. Demand is nothing but 320 megawatts. So if you can take lambda, it's 1 by 1 plus 1 by 2 plus 1 by 1.4, and bring all the parameters to the right hand side. So I have 320 then bringing here it will be plus 215 plus 270 by 2 and plus 160 by 1.4. Okay. So reducing this equation, I have this alpha coefficients. Okay. The coefficient of this is going to be 2.2143 and this comes around as 784.2857. Okay, on simplification you get lambda value is 354.193, that much rupees. Okay, that much rupees per megawatt hour. Okay, so this is the calculated value of lambda. So with this value of lambda, substituting in your equation for P1, P2, P3. So you can substitute this value of lambda here and we have to see the corresponding values. Okay, so with this value of lambda, we'll get for case 1, your P1 is going to be 139.193 megawatt. P2 is going to be 42.09 megawatt and P3 is going to be 138.709 megawatt. So we see that here the inequality, they have mentioned you what is the minimum power and the maximum power. Minimum they have mentioned as 39 megawatt and the maximum they have mentioned as 150. So we find that all the three plant generation is well within the limits. So we don't have any issue. The inequality constraint is satisfied. So well, it is well within the optimum scheduling. So this is based on your equal lambda criterion. We have done this problem. Now the same thing will continue with the case 2. Okay, so case 2 where the load has been changed. The load has been changed from 320, it is being changed as 200 megawatts. Okay, it is changed to 200 megawatt. Still the same power balance equation. This whole equation will remain the same and this will become 200. Okay, so this all will remain the same. This is going to be 200 and we have to find out the corresponding value of this. Of course, this equation also, this lambda also will remain the same, which will be 2143, this. Okay, and this will change. Okay, so this it probably comes around as 664.2857. Okay, and for this solving your value of lambda, the lambda value comes as 300. Okay, so it is a bit reduced for this case because your load is reduced, automatically lambda also has been reduced. So lambda is now 300 rupees per megawatt hour. Now, when I have this value of lambda, once again you can get what is, substitute this value of lambda in P1, P2 and P3. Okay, now corresponding value of generation. So case 2, we have as per the generation, to satisfy a demand of 200 megawatts, we'll get P1. Okay, so P1 we get it as 85 megawatt. This is 15 megawatt and this is 100 megawatt. Okay, so substituting this value of 300 here, P1. So if you see this P1 plant and P3 plant is well within the limits. It's 85 megawatt and 100 megawatt. But what about your P2? P2 is only 15 megawatts. It is because the minimum limit they have mentioned is 39. So it is violating the limit. So since it is violating the limit, what is the rule? It cannot go for a generation lesser than its minimum generation. So I have to fix it with the minimum generation. So the strategy to be adopted is, I'll fix this. Okay, delta P2. Okay, P2 has to be fixed. Okay, fixed at its minimum value, which is 39 megawatt. Okay, so P2 has to be fixed at 39 megawatt. So in this case, what happened? You have to find out. So the remaining load has to be distributed among the other remaining units. So with P2, okay, so we'll modify this case. P2 is fixed up with 39 megawatt. Okay, so I have to subtract this 39 megawatt from your demand. Okay, so what is it? It is your 200 minus 39, which is going to be your 161 megawatt. And I have to, since I have fixed up your P2, further I have to have only the load has to be distributed among the remaining two units, which is your P1 and P3. So I can remove this. Okay, it goes with your P1 generation with this equation and P3 generation with the same equation. And the demand, subtracting a 39 from your 1200 will be only 161 megawatt. So this also reduces. This is, so this coefficient will change now. Okay, so it is going to be your 1 by 1 plus only 1 by 1.4, and here it is going to be your 161 plus 250 plus 160 by 1.4. Okay, so here it further reduces. Okay, so this value of lambda is going to be 7143, and this further it will get reduced, and this value it is some 490.2857. Okay, and with this values, the value of lambda is still reducing, and the lambda you have come around as 286. Okay, this comes around, the lambda is 200. Now, what happened? I have your lambda as 286 with P2 already fixed. So I have to only calculate for P1 and P3. So substitute this value of lambda in P1 equation as well as in P3 equation, and let me go for case 2 modified, isn't it? Case 2 modification. Okay, and this is being fixed at 39 megawatt, and I have to see with this value of lambda. Here you will get P1 is going to be fixed up at 71 megawatt, and with this value of lambda at P3, this P3 is getting at 90 megawatt. Okay, so your total load is 200, 71 plus 39 plus 90, total load comes around 200 megawatt. Since P2 has violated the limit, we fixed up at its minimum generation, and the load was further distributed among the remaining two units, and we are able to satisfy the load. Okay, so this is how the economic load dispatch has to be done with this, even considering your inequality constraint. Yes? Okay. Next, we shall go for your third case. So let's see for the third example. So here it is mentioned with the two units in the same plant. They have mentioned you what is the incremental cost of the two different plants is mentioned. But here to be noted, the load is not a fixed load. The load here varies right from 50 to 250 megawatts. So it's a varying load on the system. And they have also mentioned what is the inequality constraint. That is, we have to have the minimum generation has to be maintained at 20 megawatt, and the maximum generation has to be maintained at 125 megawatt. And we have to see how the load has to be optimally distributed with this among the two units. Okay, so let us come here. Now, let me have the incremental cost of the first plant is mentioned as 0.8 P1 plus 160, that much rupees per megawatt hour, and I have got the incremental cost curve of the second plant is given, second unit is given as 0.9 P2 plus 120. Okay, that much rupees per megawatt hour. Now, of course, if you see from this, we always know that your first incremental cost of the first plant is greater than the incremental cost curve of the second plant, and they have given the minimum limit. P minimum has to be 20 megawatt, and P maximum can go up to 125 megawatt. Okay, and the demand, this varies right from 50 to 250. That is the two plants, two unit, each with 125, 125, it can go up to 250. So So this is your demand nation. Now we can find out the incremental cost of the first plant is greater than the incremental cost curve of the second plant. So you always have a strategy that the plant or the unit with the lowest incremental cost has to be loaded first. Okay, then with the plant with highest incremental cost. So in that case, you have to maintain P1 is maintained as 21 because the minimum generation on this plant is 20 megawatts. So you have to have it the minimum generation. So the P1 unit, the unit 1 can go with the minimum 20. So you see what is the load on the minimum load? It has to start with 50. So out of which 20 is being allotted to the P1. So remaining P2 will be your 50 minus 20, which is 30 megawatt. So initially I will start with P1 with 20 megawatt and P2 with 30 megawatt. Now if we compute your incremental cost of the first plant with 20 megawatts. So if you have your P1 as 20, this incremental cost comes as 176 rupees per megawatt hour. Okay, and P2 when maintaining 30. So substitute your P2 equal to 30. The incremental cost is only 147. Okay, it's 147 rupees per megawatt hour. Okay, so the incremental cost curve of the first unit is greater than the incremental cost curve of the second unit. So what is the strategy? Till this plant, okay, so till both your plants find an equal incremental cost, I have to start loading only on your plant 2. So we fix up your P1 as 20 and P2 will be loaded initially till both this incremental cost becomes equal. So if we see this, what happens? We have to see the loading. So from the equation, of course, from the incremental cost, we can find P1 is lambda minus 160 by 0.8 and P2 is lambda minus 120 by 0.9. Okay, so this is your, from the equation we can write. And now what I have to see, so the load on the unit 1 is going to be 20 megawatts and the load on the unit 2 is going to be 30 megawatt. And the sum, 20 plus 30, this will be the total load on the plant. Okay, 50, this load. So I start with a load of 50 with P1 20 and P2 30. So the low plant or the unit with the lowest incremental cost is loaded more than this. Okay, so this is the case. So the plant, the unit 2 has got 147, whereas the unit 1 it has got 176. So till the incremental cost is varying from 147 to 176, I load only your unit 2, where the unit 1 remains the same at 20. So if we substitute 176 here, okay, with a value of 176 for this plant 2, we find P2 will come as 62.2. So you can see this 176, this is remaining 20 itself, whereas this becomes 62. So here the total sum will be 82.2. So right from 50 megawatt to any load till 82.2 megawatt, P1 will be loaded only 20 and variation is brought only in your P2. Okay, so any load between 50 to 82.2, you can vary only your P2. The loading is done only on your unit 2. Okay, then next we'll see how this progresses, because I have to vary the load totally from 50 to 250 megawatts. Next we'll, so now here when at 176 both plant it has been same incremental cost. From here onwards I can start loading both the plants. Now let me go, if suppose 180, I maintain 180. So 180 here for both this, we have to see P1 will come 25, whereas 180 with this P2 will come 66.6. Like this, we increase slowly from 180, 190, 200, 210. Like this, we increase the value of your lambda and find the corresponding values of P1 and P2. Now, like we can have sum of P1 and P2, we get the total critical load of the system. So here we find that at 230 somewhere, this becomes 122.2 and this is becoming 87.5. Okay, so your loading is more done on your P2, which has got lowest incremental cost. And what is the maximum limit? It is 125 megawatt. So this is to reach your maximum limit first. Then only it will be reaching this plant unit will reach its maximum limit. So next, if suppose I increase this to incremental cost from 230, then if I move on to 232.2, if lambda value is 232.2, with this value of 232, what happens? Your thing it has reached, your P2 has reached 125 megawatt. So the maximum is reached. Further, I will not be able to load your unit 2. Further loading is only done on your unit 1. So we start to loading your unit 1 till it reaches your maximum. Then we can find when this is loaded. Find once again when incrementing the value of lambda, substitute in the equations. So you can get P1 alone can be loaded with lambda. So different values of lambda, substitute here, you will get the value of P1. So here this is maintained as 125 and this is slowly incrementing, it reaches 125. So at this cost we find both are loaded to its maximum and the maximum load that could be delivered is 250. So this is how the plant load distribution takes from 50 to 250 megawatts, and this is a sharing among the two units. Okay, so this is a tabulated result and this could also be well shown in a graphical representation. So this shows the graphical representation of how these two units are loaded from a load of 50 megawatts up to 250 megawatts. So here we see that since the first plant has got a higher incremental cost, I try to maintain with only the minimum generation for this plant. So it's only loaded. So first load is 50. Okay. So where 20 is being taken by your unit 1 and 30 is taken by your unit 2. After which till this has got a incremental cost of 176 and this has got 147. So till this particular plant also reaches 176, I try to load only your plant 2 or unit 2 and this is maintained with same 20. After which when both the plants are 176, from here onwards both the unit are being loaded. Okay, and we can find that as the loading is done, when it reaches here, this particular plant unit that reaches its maximum generation 125 megawatt. After which we'll stop loading your P2 unit, will be loading only your unit 1. Okay, so unit 1 is slowly loaded till 260 or somewhere in both. This also reaches 125 megawatt. Now 125 both load will be 250 megawatts. So this is how the load sharing is done among different generating units within a plant. So we have not yet considered any transmission losses here. So this is how the load distribution is done or optimal scheduling is done for different units within a plant. Okay. So next session we will be seeing what will be the economic scheduling among the different plants considering the transmission losses. Okay. Thank you for this session. Thank you.